Okay, so shall we start? So that was supposed to be a welcome talk for me joining the Links lab, but I joined like in March, I think, last year, but it took, for obvious reasons, it was pushed further and further, so I'm giving it now. So the well, in general, my area of research is distributed fault-tolerant computing, and this relates to building algorithms that run in a distributed system and that tolerate failures of components of those systems. And what are the components? Could be either computing units, which in our parlance we say it's processes. We call them processes, and it could also be the communication primitives, for example, communication channels. For a long time, I've been doing this, building protocols which anticipate failures that are correct despite failures of those components. But recently, well, not that recently actually, but for some time, for quite some time already, I've been looking also in the algorithms that somehow leverage the ability of detecting failures a posteriori, so somehow detecting that a given component of the distributed system deviates from its expected behavior. And well, the expected behavior for us, it's an algorithm. So we assign an algorithm to the system. Each computing unit is assigned with its own algorithm, and if the unit doesn't comply, deviates from the algorithm, we call it a failure. And we try to see if we can detect these failures, and we use it in the algorithm. So in addition to tolerating failures, we also try to detect them and make the system participants accountable for their actions. And that's where accountability comes into play. Okay. So the general motivation for all this story is that, okay, we need to share data at a large scale. And as long as we have this large scale and we have a lot of users of the shared data, we come to the problem of vulnerability towards failures and asynchrony. So the communication between the components of the system doesn't have to be necessarily synchronous, which is very hard to maintain at a large scale. And the more units we have, the more likely that the units will fail. There could be hardware failures, which we call crashes, just because of some hardware failure, the process cannot continue taking steps of its algorithm, or it could be some security attack, or maybe some transient software bug or stuff like this. Well, I'm going to claim that existing techniques which we have are short in dealing with failures and asynchrony in an efficient way. We also want to maintain some level of performance. Otherwise, why would we need these systems? So new techniques are needed, and one of those techniques which I'm going to focus on is accountability. And by the way, don't hesitate to ask your questions online. And it's actually a great pleasure for me to see that many people in the audience. It's been a while since I physically was giving a talk to that many people. Nowadays, if we talk about a computing system, we typically talk about distributed computing systems. And one instantiation of this claim is the recent rise of industrial databases, NoSQL, SQL databases, which are supposed to serve data on an enormous scale. And the main challenge in this kind of protocols is to guarantee consistency, to make sure that data you read in the system is consistent, is correct, availability, that you can access the data, and the performance, despite failures and asynchrony. And this is the major theme of all this area of research, is that you have failures and asynchrony are the main enemies which we want to defeat. So failures talk about components which may fail, and the asynchrony talks about the bounds on communication and computing, relative computing skills. So an interesting thing is if you make no assumptions about the bounds on communication, I'll just say that processes in the system can communicate, but we don't say anything about the guarantees that the communication channels provide. And at the same time, we want to tolerate failures. what can be computed? What algorithms, what fault-tolerant algorithms can be designed in a purely asynchronous setting? That was a major question for quite a while, and it turns out that there are some eventual safety guarantees which can be provided in the absence of synchrony and despite failures. And there are very interesting research which somehow tries to characterize what kind of eventual predicates we can compute on the system state. It could be semi-linear predicates. There is a conflict-free replicated data types which can be implemented in such way. Well, recently we've been shown that some variants of cryptocurrency can be implemented asynchronously and fault tolerant. Some interesting abstractions like lattice agreement can be implemented. Well, consensus total order. Well, one of the major results in distributed computing is that consensus doesn't have asynchronous fault-tolerant solutions. As long as at least one process in a large system can fail, no deterministic protocol can achieve consensus in the asynchronous way. And that raises the question of fault detection. Okay, so we have some abstractions which can be implemented in this intersection, some cannot. And the consensus is a very demanded abstraction because it's actually core of many systems, in particular blockchains. And the question is what kind of fault detection mechanism we need to provide so that we could implement it. So in the fault model, well, fault models we consider here, they start with the simplest crash faults. They're benign in the sense that there's no malicious mind behind it. It's just some hardware fault. To the other side of the spectrum, Byzantine faults, where we make no assumptions about the behavior of Byzantine components. So the crash fault means that the process just stops taking steps indefinitely. A Byzantine process can perform any action within the model, but it's not restricted by its protocol anymore. So how we deal with faults? We can either prevent faults by masking them. Yeah, and the major approach to deal with this, to prevent faults from happening is to prevent faults from affecting the system properties is to replicate the data and to engage in synchronization protocols between the copies of the data so that all these copies are sort of up to date. And to detect failures, we just try to see who misbehaved. And then we can punish the process for misbehavior, for example, by removing it from the system and ignoring its messages. So these two approaches are, I believe, they are complementary. So in many systems, we want both sides, we want both prevention and detection. And while masking fault tolerance mechanisms are comparatively well understood, detection is not. Try to fix it to some extent. So in this talk, I will describe the context. We typically talk about replicated services, yeah, so it's a specific class of distributed algorithms which try to implement a specific service which is specified as a state machine, a sequential state machine. We could try to replicate it in a distributed system so that the clients do not distinguish the difference between the service running on one server from a distributed system. We start with crash faults, and we'll discuss how crash faults can be detected. Here we will come to the classical notion of failure detectors, and then we will try to understand how Byzantine faults can be detected, and we'll discuss a generic fault detection process problem. And finally, we'll focus on a specific aspect of accountability, which relates to detecting faults which affect the system properties. So we know what the system is supposed to implement, and we see if the high-level desired system properties are violated. Then we try to originate it back, bring it back to the originator, find who misbehaved, and detect. And depending on who we detected, we can reconfigure the system online. We will also touch the aspect of reconfiguration. So this work is a joint work of many people, with many of my colleagues like Rashid Garawi, Peter Ruschel, Andreas Heberlen, Thibaut Retour, Sarah Touche-Pergiovanni, Joao Bezerra, Lucia Freitas, Andrei Tankich, and Joao Andrei actually are here. So I will just mention the names, and then later on it will go without saying that whenever I talk about our work, it's work with my colleagues. So what is the replicated service? Yeah, it's a collection of servers. These servers accept requests from external clients. Usually it's convenient to treat the system as servers and clients. So clients are logically separated, sometimes physically separated from the servers. So they issue requests, operations on the shared data, and the servers accept these requests and process them and send back responses to the clients. And we, as usual, whenever we implement the system, we want certain safety and liveness properties to be satisfied. On the liveness side, we say that if the client is persistent, it is active enough, sends its request. So it should supposed to receive responses back. And on the safety side, we want to make sure that the responses are consistent in the sense that clients cannot distinguish these responses from responses that could have come from a correct sequential server, which just receives these requests and executes them in the same order. Okay. On the model side, so this is more like an application. So this is what the system we want to implement. Let's see where we want to implement it, in what environment. So we assume that we have servers connecting and clients connected via communication channels. So the channels are reliable in the sense that they don't lose messages, and they don't create messages, they don't duplicate messages. And the fault model, we go from crash to Byzantine. Actually, I didn't mention one intermediate model, which is called omission model. There, instead of performing incorrect actions, a faulty component can omit performing some action. Just, for example, you send a message, but the message is lost. So this can be seen as an omission failure. And we have different synchrony assumptions. And here we have different degrees of synchrony, from synchronous, where the communication channel provides some fixed and known a priori bound on communication delays. And processing is also bounded. So in the sense that, yeah, it takes some bounded time for a process to perform a step of computation. We can go to partially synchronous models where bounds, for example, exist, but we don't know them in advance. So we cannot really build our algorithms having this knowledge a priori. We have to adapt it. Another variant of an eventually synchronous model is to say that there are some bounds which only holds eventually. Yeah. So for example, we know the bound, but we never know when the bound holds. We only know that it holds from some point on, and we don't know when this point arrives. And this is called global stabilization time, but it's unknown to the process. And finally, asynchronous, we have no bounds. We cannot make any assumption about the communication delays and processing delays. And an interesting question here: how much synchrony we can provide to the system to solve a given problem? I mean, of course, the most popular problem in this domain is the problem of consensus, how to make processes agree on something. And this brought to life the notion of a weakest failure detector, which was introduced by Chandra, Hatzilakos, and Toik. And of course, the first weakest failure detector result was for consensus. So what is a failure detector? So yeah, here's our model. We have 3 processes, but additionally, we assume that every process, P, Q, and R, has a local failure detector module. So it's an oracle, it's a distributed oracle. Every process has its own instance of its oracle, and this oracle provides some hints about who's faulty, who's not, in some form, encoded somehow. Actually, the model allows quite wide variations of failure detectors and the different formats in which this information can be provided, except that this information is only based on the failure partner, who is faulty, who is not. It does not depend on the action which the processes take within the algorithm. And that distinguishes these crash fault detectors from Byzantine fault detectors. Actually, we should know the algorithm before we detect a failure, because a failure literally is deviation from a given algorithm. Okay, so these hints are coming from the failure detector modules. And this information can be used to partially order failure detectors. We can say that one failure detector is weaker than the other failure detector if one can emulate the other. There is a distributed algorithm that collects information from the modules of G prime and sort of imitates the module of G. So it collects some information about failures provided by the given failure detector G prime, and somehow provides information which D could have provided in specific execution. Okay, that means that every problem that can be solved with D can be solved with D prime, because I can use this reduction and compose the algorithm using D with the algorithm which implements D and solve the same problem. Okay, so that means that D prime is as strong as D, or differently, D is weaker than D prime. And now we can define the weakest failure detector for a given problem. If well, this failure detector solves the given problem, and it's weaker than any failure detector that solves the problem. So there is an algorithm that solves the problem using D, and if there is an algorithm solving the problem using D prime, then D must be weaker than D prime. And in a sense, D provides the minimal information about failures that allows us to solve the given problem. Okay. And if we talk about the most celebrated weakest failure detector results, I guess there are two. One that shows that a specific failure detector is necessary to solve consensus. And actually, it's also necessary to implement read-write shared memory in the distributed system. If you want to emulate a sort of a read-write shared memory, a read-write register in the distributed system, we require this failure detector. It's called a quorum failure detector, and it's denoted by sigma. And intuitively, it guarantees that it outputs sets of processes, which we call quorums. And it is required that every two quorums output by every two processes at any moments of time should intersect, should have at least one process in common. And eventually, from some point on, every quorum output by process should contain only correct processes. Yeah, so it is a failure detector because it depends on the failure pattern, it depends who's faulty. From some point on, it is forbidden to output faulty processes in the quorum. Okay. So typically, it guarantees two sides of implementing shared memory. On the safety side, it guarantees that no decision unless a quorum is consulted can be taken. For example, no value can be considered to be written in the memory unless the quorum of processes agreed to store this data. Yeah, and that makes sure that every future read using a quorum will see the data. And the liveness that, eventually you will hear from some quorum. Eventually, you will guarantee that some quorum will contain only correct processes and will respond. Okay. And yeah, so you can also show that this is necessary for consensus, actually, for the same reason, because in consensus you cannot decide on a value unless you consult a quorum. Because if you don't consult a quorum, then it is possible that two processes decide on different values completely independent. Okay, so this is necessary. I didn't say it was sufficient. Now, to make it to find a sufficient failure detector for consensus, there is another side of it, which basically takes care of the liveness side of consensus now. And this is omega, which is so-called a leader election failure detector, which at every process outputs a process identifier, a leader. And for a while, it can output different leaders at different processes. For example, it can also output incorrect processes. So it's not really leader because it's faulty. And but from some point on, again, the point we don't know when exactly, it stabilizes on outputting the identity of the same correct process. So it eventually elects leader, but we don't know when. It turns out that this is sufficient. Well, the combination of sigma and omega is sufficient to solve consensus. And also, omega is necessary to solve consensus. It's weaker than any failure detector that solves consensus. And yeah, I guess I should have changed the order. I put sigma first, but maybe because it's slightly simpler. This one is one of the most fundamental results in distributed computing, which shows that omega indeed is necessary. And the proof of this necessity is one of the most beautiful proofs I know. So this is by Chandra Hadzilakis and Toy. It's been devised more than 25 years ago. Okay, so there is an interesting link to this folklore theorem. It's called CAP theorem about distributed computing, coined by Eric Brewer also quite some time ago. That no system can combine consistency, availability, and partition tolerance. Yeah, so if you want to be consistent, we want to make sure that the system reminds some centralized server. Yeah, and at the same time, we want to make sure that every request to the servers eventually returns availability. Then we cannot make sure that we cannot tolerate partitions. We cannot split the system into independent components. So this is you can either get consistency in partition tolerance, or you can get availability in partition tolerance, or consistent availability without partitions. And typical systems, well, the major goal is to provide consistency and availability. So we try to fix partitions somehow. I mean, intuitively, this sigma failure detector exactly fixes partitions. This is exactly what somehow makes sure that you don't have partitions. So these intersecting quorums guarantee that no two subsets of disjoint components of the system can make progress independently. Okay. And yeah, Gilbert and Lynch later try to formalize this and show that you cannot implement a register in a synchronous crash-prone message passing system with partitions. Okay, so this was about consensus. Well, consensus is you can see it as consistency which always holds. We can relax this requirement. We can say, okay, let's imagine that we don't want always to be consistent. We don't always to see the same state in our implemented state machine. Let's imagine that we want this property to hold eventually from some point on. And this can be factored out as the problem of eventual consensus. So you have consensus instances invoked one by one, and for some bounded, well, some finite but possibly not a bounded number of times we may disagree, but from some point on we always agree. Yeah, from some point on, every next instance of consensus brings us the same decision. And it turns out that omega it is necessary for this problem too, not only for consensus but also for eventual consensus. Yeah, so it's sufficient in the sense that eventually you use this omega as a leader for each instance of this in this series of consensuses, and eventually the leader stabilizes, and that's exactly what we need for solving consensus. But it's also necessary. And here we actually use some power which was not used before in the original proof to emulate omega from any eventual consistent algorithm. Okay. So if you want to know more about failure detectors, there's a nice survey which was already quite dated, but at the time it was the most up-to-date summary of results in the area, together with the sketch, I think quite intuitive, of the C-sheet, the proof of that consensus is necessary to that omega is necessary to solve consensus. Okay, any questions so far? Okay, that was about crash fault tolerance. Yeah, so now to slightly more recent stuff, where we talk about systems which are subject to Byzantine failures. And we talk about fault detection problem. Okay. So there was not so much written about Byzantine faults, about detecting Byzantine faults. So there were some attempts to provide generic accountability in those systems, more like on this system side. There was some real system which tried to do it on the fly, and there was some systems paper trying to implement and reason about complexity. And I mentioned this paper slightly a bit later. And then there was also a couple of papers which would try to treat specific algorithms, like take the specific algorithm, for example, consensus algorithm, and try to see how to detect failures in this specific algorithm. So it's not that generic anymore. Okay, so we talk here about the general domain of accountable computing. So we try to understand what kind of deviations from a given algorithm are detectable. Turns out that not every Byzantine fault is detectable. It's not that surprising, because if you can just imagine a process silently doing something on its local state without affecting any other process. Of course, it's a deviation, but it's not completely silent to the rest of the system. And a more interesting question: how much does it cost? What is the overhead we need to impose on the algorithm if we want to make the algorithm detectable? Here I refer to two papers which were published quite some time ago, where the first paper was more like a system with generic accountability mechanism. The second one was actually trying to formalize the problem solved by the system. Okay, so we refined the model a little bit. So we assume that the system is asynchronous. And in the asynchronous system, we can just treat an execution as a sequence of events. Events coming from different processes. So the event here is characterized by the identifier of the process, which takes this event, set of inputs which the process accepts, and the inputs could be either the inputs coming from the application of the process, from its user, or from the network. It could be a message which the process receives, and the set of outputs of the process. We call it could be either the output to the application or the set of messages the process sends in this step to other process. So every process somehow is between its application, which provides inputs and accepts outputs, application inputs and application outputs, and the underlying network, which is the medium to communicate with other processes. Okay. And now the distributed algorithm is just a collection of automata. So you assign an automaton to every process I, and in this automaton, we need to specify the set of messages the process can send, the set of terminal inputs it can accept, or application inputs, terminal outputs it can provide, and the state transition function, the initial state, and the set of states it can take. And we assume that this automaton is deterministic, meaning that for every input and state, it provides exactly one output and state. And we know this correct if it follows the algorithm, roughly speaking. So what is fault detection? Imagine that we have some algorithm and we have this network of 4 processes. And in this algorithm, there is a process C, which is supposed to receive 2 inputs from A and B and provide an output, which is the sum of these 2 inputs. Yeah, well, in a normal execution, we should see something like this. But in case the process performing the computation is Byzantine, we can see something else. But again, here, by observing this output here on the D side, we cannot know. We may even miss the fact that the failure occurred. And even if we detect the failure, we cannot attribute this failure to any particular process. Okay, but ideally, we would like to see, in this case, we would like the correct process to output an indication, saying that C is faulty. Okay, so the fault detection problem informally is defined as follows. We say, given an algorithm and a set of faults to detect, a fault class, I will specify what a fault is. A fault roughly is a deviation from A. Goal is to see if a specific fault occurs in this fault class. Correct nodes output a list of faulty nodes. Yeah. So intuitively, it's like we're given the algorithm A, yeah, the algorithm which is under detection. And we build an extension of this algorithm which does exactly the same as like all the actions of the original algorithm plus fault detection. Yeah, so it behaves like A, but plus it detects faults in this fault class F. And to solve a fault detection problem means to find a generic transformation which, given the algorithm, provides another algorithm that is a countable version of the given. Okay. So extension is also the extension of A, which we call A prime, is also an algorithm. So this extension should agree on the inputs. It should provide the same outputs plus, well, intuitively fault detection. And there are some mappings between the states and the messages, so that in a way you can, given any execution of the extended algorithm, find a map, well, to map it to an execution of the original. So the intuition is still the same. So you observe what's happening in the extended algorithm, and you can sort of project some events of the extended algorithm to events of the original one. But some events, of course, are not coming from the original algorithm because they are related to fault detection. Okay, so now I promised to define a fault instance more precisely. So a fault instance is a tuple. So we have again, a fault is deviation from the algorithm. So we need to provide an algorithm. Okay, so it's an algorithm. Then you have to provide the set of correct processes, because what you can detect, what you cannot detect, depends on who is correct. Sometimes if you only focus on very small set of correct processes, then very few failures can be detected. The larger is the set of correct processes, the more events you can observe. The more events the correct process can observe, and the more faults can be detected. And you also can have a set of suspects which should contain at least one fault. So this is what's happening there. Okay, and this is all relative to the execution. Yeah, so in given execution, this is the algorithm, this is a set of correct processes, and this is the set of suspected processes. Because you don't want to waste your time and energy, you want to suspect a set which contains at least one fault. So to justify the fact that the fault instance must specify the set of correct processes, imagine that you have something like this here. Yeah, you have two inputs, 9 and 4, and output which has nothing to do with the inputs. Yeah. So then if we only consider this set of correct processes, then we cannot really attribute a fault to any particular process. We need to suspect a subset. In this case, we probably would like to suspect A, B, and C. Okay. Otherwise, if you include A and B, then we can actually detect C to be misbehaving. Okay. Otherwise, we can also quantify who is faulty if we see necessarily that the sum of two values is beyond the expected value. So in this case, again, we don't know who's faulty. But at least we can zoom to the subset of A and B. Okay. So now we can formulate the problem more precisely. So given the fault class F, find the transformation of fault class F is the types of misbehavior we're interested in detecting. Find the transformation that maps any algorithm to its extension in a way that if there is a fault instance in this class, at least one correct process will permanently output it. Output at least one suspect in this desired set of suspects, and the accuracy that if you suspect someone, will at some point, if the suspected process is correct, it's no longer suspected. Occasional mistakes are okay and in a way inevitable in an asynchronous system. And eventually, correct processes, they agree on the set of suspected ones. So given this definition of the problem, the next question is what kind of fault classes are actually detected? So it turns out that not everything can be brought to this problem and implemented in the asynchronous system. So imagine that we can try to visualize the set of all possible fault instances. And we can actually separate instances which are impossible to detect, for instance, which are possible to detect. So first of all, the first thing we filter away is the faults which do not affect correct processes. So from the perspective of correct processes in the system, they never happened. In the actual execution, they did, but the correct processes are not able to observe. So those can be strictly shown non-observable because there's always a correct execution in which correct processes have the same experience the same events. Then there are ambiguous fault instances because sometimes you can be too ambitious and you can say, okay, I want to detect this particular process to misbehave. But it turns out that in some cases exactly the same state is observed by correct processes if the other process is misbehaving, not this particular one. So then those ambiguous fault instances are not able to be detected. We are not able to detect them if you want to preserve the accuracy and completeness properties. And finally, you have commission faults. So those are probably the easiest to behave because you can just map the observable behavior of a process to its expected behavior specified by its algorithm, and you see the difference. Like whenever you perform obviously an action which you are not supposed to perform. Like one example is in many consensus algorithms, you vote for values. Yeah, you receive ballots saying, okay, let's decide on this value, and you say if you don't see any conflicts, you vote for it. And if it turns out that you voted for two different values in the same round of the algorithm, obviously you committed a fault, and this fault can be actually detected. Everyone who see 2 volts coming from you can detect this failure. So here we implicitly assume that every action performed by a process is signed, and the signature can be forged. That's a typical assumption behind Byzantine fault-tolerant protocols. And finally, we have omission faults. Yeah, the omission faults are faults where the process doesn't take an action it's supposed to take. You receive a ballot, you never respond to it. This is an omission fault. So it's some kind of crash fault, except that you can respond selectively. You respond to some processes, but not to the others. And this thing, yeah, you can also detect. Again, detect probably eventually, not you can, in the asynchronous system, you can temporarily suspect someone to commit to perform an omission failure while the process is just slow. Yeah. And, you cannot avoid these cases if the system is asynchronous. So what is the overhead of detection? So there is this very rough analysis coming from this old paper we published with Andreas some time ago. So somehow we want to see how many extra messages every event performed within the execution of an algorithm incurs. How many extra messages you need to put on top of it to provide accountability. So here we take this assumption about the number of faulty nodes, and this is a typical assumption here, because in the algorithms we envisioned back then, we assume that every process has a certain number of witnesses. Every action which a process performs can be challenged by a set of witnesses, and this set of witnesses must include at least one correct process, which actually means that the set of witnesses should include at least f+1 processes in the system tolerating f failures. Because if it's less, then all witnesses for a process can be faulty, and then nothing can be detected. So for commission faults, we had this bounds proportional to f. For omission faults, which have something slightly larger. And what's important is that we want to guarantee that whenever we detect the failures, every correct process eventually detects it, then it incurs for the quadratic complexity for omission faults, because we need to engage into some form of reliable broadcast to reach everybody. So it's an impressive overhead, and this overhead actually it's for every event, which means that can be quite a burden. And intuitively, this motivates the last part of this talk, where we talk about detecting failures in the application-specific way. So we want to don't rush to detect any kind of misbehavior. We just zoom into the outputs of the system. We see what outputs it provides given the inputs, and if the outputs are not consistent, deviate from the safety property of my system, then we detect the origin of the safety violation. And it turns out that this less ambitious formulation of accountability is more realistic. It's easier to implement. And in fact, this also gives us a way to think of a system which is in a way self-healing. It detects safety violations, reconfigures itself by evicting misbehaving parties, and moves on. Yeah, converges on the state, moves on, and then if there is another violation, again it reconfigures, moves on, and so on. So it's an online process which can have transient periods of inconsistency, but then brings back to the. So it somehow tolerates failures and also detects failures a posteriori. What is the idea here? So here I give the just an illustration. So we only detect commission faults, faults which are obviously incorrect actions that affect safety. So that was also considered quite some time ago in the case of consensus, but recently there was a system proposed to which explicitly spells out this notion of accountability, and this is an algorithm which implements accountable consensus. So here the idea is very simple. So imagine that you have clients and you have some replicas, and the clients need to agree on something. For example, in this case, they want to agree on the first command to be executed on the replicated state machine. So they both provide some commands. So let's say one user provides command A, and the response from the system involving this subset of servers says, okay, A, go first. But concurrently, you can have another user issuing command B, and it also involves a set of servers. And based on the outcomes from this set of servers, B should go first. Okay, how can be? Can only be if the intersection of these two subsets contains only Byzantine processes. So, in fact, you may have a situation when these two commands are ordered inconsistently to be reversed by the two different clients. Yeah, so then temporarily we see that the two clients observe inconsistent state of the system. But then, since we assume that communication is reliable, these clients would consult with each other, and we realize that, okay, a posteriori, something went wrong. So in this case, you say, okay, these two guys are incorrect. And in fact, since all messages are signed, and we have this assumption that, yeah, the certificates are held forever, for each decision held forever everywhere. So then you can actually identify the intersection of two certificates, or certificates, signed messages by all the servers confirming that A should go first, and signed messages from everybody here so B should go first. We should do two different signed messages by these two guys. Okay, so this is a proof of misbehavior. Okay, so then the next question is, okay, what do we do about this? How can we deal with this? It turns out that, well, we can, the same way we can detect failures, we can also reconfigure the system based on this detection. And here, well, I will mention a few works which talk about reconfigurable systems which allow the clients to invoke reconfiguration requests. Yeah, there were some, and conventionally it was all based on consensus. So you would run a system, maybe even if the system state itself doesn't require agreement, such as storage. Storage doesn't require agreement among the processes, but whenever you have some reconfiguration request, you try to agree with everybody on what is the set of servers from this point on. Okay, so that's and then there was a more general approach which said, okay, maybe the state does require consensus, and we use consensus for agreeing on the system state on the concurrent requests and on the configuration too. But then there was an interesting observation that you could actually avoid solving consensus if your goal is to reconfigure the system. There is an asynchronous reconfiguration protocol which is using a different abstraction which is called Lattice agreement. So it's a weaker form of agreement, and I will say a few words about this. So it's, in a way, you can see it as an alternative for consensus. Consensus provides some kind of totally agreed upon order on the system states. Yeah, so you agree, this is the first system state. Then we agree on what is the set of commands applied to this first system state, and get the second one, and the third one, and so on. So it's a complete agreement on the way the system evolves. Okay, so you can see it like this. So your different participants can live in different times, but the order in which the system state changes is the same everywhere. In contrast, lattice agreement is some kind of you agree on a totally ordered set and some partially ordered set. So you have states, and you don't really know like exact transitions. You, for example, you say I started in this state, then I ended up in the state which combines these two requests, and then you end up in the state which combines these four requests. And it turns out that maybe someone else can jump directly from here to here. Okay, or someone can actually find out in the final state. So in fact, this, you don't really know exact state transitions. And in a way, you can see it as, if you have concurrency, if you have two requests concurrently applied, then you can actually see your state as a composition of these requests. You don't really know in which order they applied, but so what the only thing which you require from this abstraction is that the states you reach, all the states reached by correct processes are totally ordered. And this is the case here. Well, if the order is the set inclusion. Here, indeed, if you take any state observed by any process, any two states are related by containment. So one is a subset of the other, even though we don't really know in which order these requests are applied. So formally, any lattice agreement algorithm assumes a lattice. Lattice is a partially ordered set with a specific operation, which is called the least upper bound. So for any set of values, we can find the least upper bound for this. And intuitively, the least upper bound is like a join of operations. If you think about a state in the distributed system, and you have a number of operations which try to modify the state, we have a way of composing this state, these operations in one composite operation. And there is an initial state, of course. So start with initial state U0, which is smaller than any other state. Yeah, you can go further and further. And why it's called a lattice, you can visualize it as a lattice and see it as a set of vertices, and every two vertices has a common vertex which unifies them. So the simplest example is a set lattice. So elements of the lattice are sets of, say, natural numbers. So the partial order is the set inclusion, and the join operator is just the union. Okay. You can actually model a set with the remove operation. And now the remove operation can be represented as a minus, as a negative number. So now the set of elements of a set with the remove operation would be a set of integers. And now if you look at the state, you can see values which have been added and then removed, and then you consider this element is not in the set. The operations are still the same. So the inclusion, the more updates you see, the larger set you have, and the union is still the same. Max register is a very interesting abstraction which can be used to implement many things. In particular, it's used to implement storage. So max register is used to implement the sequence numbers on the versions of data. So it's you can see it as a set defined on the natural numbers. It's actually at the same time a partial and a total order. So you have the partial order is defined just a lesser equal operator, and the union of two numbers is the maximum. Okay, and the origin is 0. And, maybe the most interesting thing, well, this might look trivial or maybe useless, and in fact, it's very useful, because what's happening here is that two lattices can be composed in a larger lattice in a very natural way. Just take a Cartesian product of the states, a Cartesian product of the operators, and you get a new lattice. You can formally prove that it's a lattice. And now, for example, you can see, take n max registers and implement an atomic snapshot. It's like every position. So you have n registers, one per register, max register per process. And intuitively, this is a version of the data which this process contains. Then, if you, for example, want to read the snapshot, you get exactly the set of sequence of vertices of versions of data for each position in the snapshot. Okay, and now, because I promised, so far it was the preparation to define the lattice agreement as an object or as a problem. So now we given a lattice, as a set of values, a partial order, and join operator. Solving lattice agreement is building a protocol in which processes can propose values and learn values. It's a little bit like a consensus. Consensus, you propose values and decide values. In lattice agreement, you propose values and you learn them. And you can learn more and more values, like because it's a long-lived algorithm which we keep proposing, keep learning. And you require that all values which the abstraction provides to you are totally ordered. Yeah, so all learned values are comparable with respect to this partial order relation. Okay. So maybe you propose values which are not totally ordered, but the learned values should constitute a linear order. Of course, the learned values should depend on the values proposed. Yeah, so this is so learned values is a join of proposed values. Otherwise, you can always stick to the region of the lattice, trivially satisfy comparability. And every value which is proposed by a correct process should eventually appear in some learned value. Yeah, so if you keep proposing something, it should be reflected in this. So unlike consensus, yeah, consensus is known to not to have asynchronous fault-tolerant solutions. Here we have an asynchronous efficient implementation, efficient also in the sense that even in good runs it performs better than consensus. And it can be implemented in fault-tolerant way, assuming, of course, like making some assumptions about failures. So here again, we cannot tolerate partitions, so we need some form of failure detector, or we assume a majority of correct processes, for example. And it turns out that this lattice agreement fits exactly what we need to reconfigure a system. So what is reconfiguration? We have a set of servers, so sometimes we say replicas, we have clients outside of the system. At some point, we suspect that some servers are incorrect and the clients propose to replace them with new ones. So this is changing from one set of replicas to another set of replicas. What's interesting here is that the clients, there are ongoing requests coming to the system. The system still uses the data stored at the servers in this configuration or this configuration. And we want to make sure that the clients which work with the data, those which are not involved in this reconfiguration, they don't see the difference. For them, it's completely transparent. So we need to change the set of servers and make sure that the data stored in the original configuration is migrated seamlessly and transparently to the new set of replicas. Yeah, so as I said, that the classical reconfiguration was in storage systems was consensus based, but since the system which we call Dynastore, in which in a way already included this ideas of lattice agreement without explicitly saying this, provides asynchronous solutions. And here I just described an explicit asynchronous solution, which is based on lattices. And here I assume that we have a configuration lattice, so a specific type of lattice, where every element in this partially ordered set should include a set of replicas. So this is an attribute, and also a quorum system. I also put it in an abstract way. So every configuration describes the set of quorums which you can use in this configuration. Of course, we require the adversary to provide this basic availability and consistency properties of this set of quorums. And some other attributes we don't really care about what are. So one obvious example is like a set with removed and added elements. So you can have plus sign saying that, okay, this is process 1 was added, process 2 was added, process 3 was added, and then process 2 was removed. So this is the configuration which describes all updates which happened so far on the set of records. And yeah, so at some point we also show that some servers were added and removed, which effectively means that there are only 2 servers in this configuration. So the union is the join operator, and the inclusion relation is the partial order. Yeah, and we can define quorums of all majorities of these members. So now, if you want to implement an object, and we describe this object also as a lattice. As I said, for example, atomic snapshot can be described as a lattice agreement on specific lattice. So we can just compose the lattice of the object with the lattice of the configuration and get another lattice. And what's remained to show is just to implement this lattice agreement using this lattice, using this composed lattice. Every configuration results in an update in a join of proposed configurations, every update should go through the quorum of each candidate configuration, and the new decided state makes all preceding configurations obsolete. And what's important here is that once my latest agreement algorithm provides me the response, okay, look, this is a new configuration. From this point on, all configurations which are strictly smaller than this one, you can give it to the adversary. You can say, okay, from this point on, the adversary can compromise them all. Because from this point on, I already know that all the data.
Okay, sorry for the interruption. It's kind of.
Yeah. So yeah. So a very nice illustration. So the thing is that it's still this algorithm needs to assume that the adversary is not too fast in compromising configurations. We expect that the configurations still maintain some quorum properties as long as they are used, and as long as they are obsolete. And they are obsolete as soon as we decide on a configuration which includes strictly more updates, we can leave it to the adversary. So the adversary, during the reconfiguration, the adversary must be restricted in a way that doesn't compromise any quorum system of configuration which could have been installed. But as soon as we agree on what configuration is, or some process decides that this is its configuration, all preceding configurations can be wasted. And this gives us a way to have this plug and play sort of reconfiguration of multiple objects, starting from sets, max registers, atomic snapshots. Well, should have this, and some abstractions which are not implemented sequentially, but still very useful, such as conflict detector, safe agreement, commit adopt, and actually asset transfer, which is our name for cryptocurrency. You can think of a cryptocurrency mechanism which is also reconfigured and detects failures. And well, we had this recent paper on accountable and reconfigurable lattice agreements, where you're at the same time you try to tolerate failures, but if there are too many failures, and too many in the sense that there are failures which affect the consistency criterion of lattice agreement, for example, make sure that achieve different decisions or different learned values which are not consistent with each other, we are not related by this partial order, then we detect it and we reconfigure the lattice agreement in such a way that the misbehaving party is removed. And, so intuitively, we, as before, we have this interface of propose and learn. So it's a common case, safety, and liveness. And then there are too many failures, beyond accountability. Beyond the number of failures we originally anticipated, we provide an accusation, the new event of the interface, and we allow the users to update configuration. Anyway, so this whole idea of accountability, I think, is quite fruitful, and I think it's going to be used, so in particular, to build what we call self-healing distributed systems. We combine fault tolerance and accountability, and we have a regular model, assuming that we have, this is our model assumptions, and the regular model run, we have always correct, safe, and live execution. But if our model assumptions are too optimistic, and in fact we have more failures, for example, than we anticipated, we detect those failures and engage in reconfiguration. And in fact, this mechanism of accountability was useful in other contexts too. So we have, for example, we can improve resilience of algorithms which were classically assumed for example, Byzantine consensus, or we can improve consistency in systems where the trust assumptions are not centralized. We don't have a centralized quorum system. We have quorum systems chosen locally by different processes, so it gives a more complicated trust. And in this model, you can actually leverage accountability to achieve some form of consistency. But it's weaker consistency than anything we talked about so far. Much weaker than consensus of lattice agreement, but still quite useful. And well, the accountability actually, in a way, again, it depends on the way we look at it. But in proof of stake blockchains, blockchain proposals such as Casper, the algorithm behind the proof of stake based Ethereum blockchain, is using accountability as incentive. So they would say, okay, if you try to propose two different blocks concurrently, you're going to be punished for that. So there's a slaying mechanism. There are a lot of open questions, again, related to cost of accountability in this application-specific model. We don't know if the algorithms we describe are in any sense optimal, or we don't even know how to define complexity in this case. So it's kind of open. So there's obviously trade-off. Yeah, the more failures you want to detect, the more expensive your accountability mechanism will be. What is the effect of synchrony? So far, we only detect failures in asynchronous systems. If the system is, for example, partially synchronous or synchronous, what kind of detection we can expect? Privacy is a very important concern, because typically when you want to account for misbehavior, you need to see the observable actions of every process, but it might be against the wish of process to keep its internal state private. So there's a lot of cryptography, I guess, hidden there. And in fact, there are interesting optimizations, and for example, consensus algorithms, which are based on threshold signatures. So instead of signing a specific message, you sign the fact that enough messages of a specific type has been received, and it's much more expensive, much cheaper to use this kind of information in large-scale communication. But this goes against the idea of accountability. Accountability, on the contrary, you want to see that this particular process does sign this particular message. So here, it's not very clear. And I stop here. So I'm sorry for going a little bit longer than expected. And if you have any questions, I'll be happy to answer. I lost everybody.
A question on the bridge or in the room?
So, but the possibility cases you mentioned are all related to safety.
The
possibility of detection.
Yeah, here we talk about safety violations. Yes, yes.
So, is there any hope with liveness violation?
Well, liveness, yeah, it's like detecting a mission. It's like someone who is not doing or not obtaining the result which is expected. It is expected of him. This,
but omission is only one kind of.
Yes. Yeah, but omission is the fact that you're supposed to execute an action, but you never execute. Yeah, and that could cause, for example, lack of outputs. Some process never outputs something which is expected. Here, yeah, indeed, this to me it sounds more like it's closer to classical failure, except that now we are in a Byzantine setting where liveness violations can be caused by incorrect actions. That is possible. This I don't know. I have no idea. You aren't here. Okay. Shall we call it a day? Do you have any questions there? I will have Fabian. Okay. Well, thank you very much.
Thank you, Peter.